Have you ever wondered about the world beyond our planet?
You know, so many things happen in our lives and we take way too many of that for granted. For example, why am I standing on the ground and not floating around? Well, you might be answering, it's because of gravity. But why is gravity a thing? How does gravity work? These questions are what we are attempting to answer in this lesson. So let's dive right into the forces of the universe. Let's start with the most familiar type of force, gravity. Like the question I posed earlier, why are we able to stand on the ground and not be floating around and be all weird? Well, you know that the answer is gravity, but did you know that there's two different theories that describe gravity, and both are equally accepted? The first, it relates to the theory of relativity proposed by Einstein. So I want you to imagine this. Imagine a piece of cloth stretched out on all sides, forming this field of flat white space. And now I want you to imagine taking a metal ball and putting it in the center of this fabric. What do you think will happen? Well, you know that the fabric will bend in towards the ball because it's stretched on all sides, and the ball has mass, and therefore it causes a curvature in the fabric. Now if we take another smaller ball and if we place it near the big ball, we know that this smaller ball will roll towards the big ball because of this curvature in the fabric. This is actually the same concept. This is an analogy to the real world, except we cannot see this fabric. It's related to the fourth dimension. This fabric is instead space-time. How cool does that sound? But the concept is the same. A mass causes a curvature in space-time, and therefore other objects will fall in towards that curve. In simpler words, matter tells space-time how to curve, and space-time tells matter how to move. That was just one theory of how gravity works. What about the other one? Well, that leads us to the fascinating field of quantum mechanics. But first, I want you to imagine this. Imagine two friends. They're playing catch, standing some distance apart, and they're tossing this baseball back and forth at each other. Except that when they catch the ball, there's a force drawing them closer and closer together until they physically touch. And how is that relevant, and how does that relate to quantum mechanics? Well, I want you to imagine this. Imagine two particles, and imagine something called the graviton. Now this graviton is a very, very tiny particle, smaller than atoms or protons or neutrons. And let's call this graviton the ball. And let's call these two particles the friends. So how do these particles become closer and closer together? By gravity? Well, it turns out that they exchange this graviton, just like how the friends were throwing the ball at each other. They start to exchange this graviton, and there's a force because of that brings them closer and closer together. And that is how the fascinating concept of gravity really works. This next force that we'll talk about, it's not something that we're quite familiar with, but it is actually extremely, extremely important to everything that we do and see. Maybe even more important than gravity. And this is the electromagnetic force. As a little bit of overview, you might have heard that when you have two charges of opposite signs, so you have a positive charge and a negative charge, then they attract, they like each other, they want to get closer together. On the other hand, if you have two objects of the same charge, say you have one positive, or one negative, and one negative, then they don't like each other. They want to get away, they repel. But have you really thought about why behind this concept? Well, let's go back to our friends playing catch example. Say that two particles represent two friends, but this time, instead of tossing something called the graviton, they're tossing something called photons. And photon is essentially responsible for everything we see today. All the light from the sun, from your lamp, those are all photons coming out. And essentially with this electromagnetic force, is that it is just this exchange of photons between the particles that allows them to both attract or repel from each other. This may seem very, very counterintuitive just because we don't see it every day and we don't understand why that might be on this macroscopic scale. Let's move on to the last two forces. Now, if you thought that the electromagnetic force was quite unfamiliar, then these last two forces will be even more strange because there's almost no way to tell that they exist from what we see around us. And they are the strong nuclear force and the weak force. Let's start with the strong nuclear force. As we talked about in the last lesson, when we have an atom, we have something very, very dense in the middle. It's called a nucleus. And it's basically a jumble of these things called protons and neutrons. Now, if you have some background, or if you notice in last lesson, I mentioned that protons and protons, they all have positive charge. But when they're so close together, how come they don't repel? How come they don't want to get away with each other? Why are they still staying in this nucleus? And this is because of the strong nuclear force. The strong nuclear force is so strong that it's able to overcome the electromagnetic force on such small scales to keep the nucleus of an atom together. The last force that we'll look at is something called the weak force. Can you just take a moment to guess why it might be called the weak force? And if you say that it is the weakest out of all four forces, then you're absolutely right. It is the weakest. So what is it responsible for? Well, it's responsible for something called nuclear decay. So when the nucleus of an atom gets too big, such that the nuclear force cannot keep it together anymore, the atom sort of breaks apart. And in this breaking apart, something strange happens to these atoms. For example, a neutron might suddenly become a proton. And the weak force is the force that is responsible for this. And similar to the other two forces, the strong nuclear force does this by exchanging something called the gluon. So the ball is the gluon. And the weak nuclear force, the particles exchange something called bosons. In fact, they exchange 3 types of bosons. So again, the ball is akin to the boson. And these are the 4 forces that govern our universe.